Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so I would like to continue. So I want to discuss actually beam. Beam example, as I promised, this is beam analysis using moment distribution method. And I will discuss how to calculate member and moment considering support settlement. Considering support settlement, okay, considering support settlement at one of the joint. Okay, at one of the joint. So E is given as 200 GPa and I is given as 50 exponent 6 millimeter 4. Okay. So if you have question, you may ask in the chat, in the live chat. If you have any question to ask. Okay, if you have any question to ask. So this is a continuous beam. This is a continuous beam A, B, C, D. A is fixed. A is fixed. A is fixed, B and C is roller, D is pin. Actually, roller or pin in beam has similar effect. So doesn't matter whether it is pin or it is roller, unless fixed. Okay, fixed has because fixed has moment. Fixed and moment. In beam, we have to neglect the axial deformation and the horizontal force. Horizontal force also will be 0. Okay. So the question is how is calculate member and moment. Member and moment if support B is settled. Okay, support B is settled. So in addition to the support settlement, beam itself has external loading. Okay, for member BC, it is subjected to 140 vertical load at which is located at the center of member BC. Okay, and member CD, okay, member CD has UDL, uniformly distributed load. Okay, along member CD of magnitude 45 kilonewton per meter. Total length is 14. Okay, AB is 5 meter, BC is 4 meter, CD is meter. Okay. Okay, let me introduce you to this. Actually, member and moment are representing this diagram. Okay, this diagram, the green one, the green. Okay, member and moment. So why we have 6? Because we have 3 members. We have 3 members and we have 6. 1, 2, 3, 4, 5, 6. One member has 2n. Okay, so we have 6. And at the beginning of analysis, the first assumption that we made is clockwise. Okay, clockwise towards member is positive. Okay, the green arrow. Okay, and each element also beside moment has also shear reaction. Okay, shear reaction AY and BY1 at member AB, and BC we have BY2 and CY1. So we should label like this, BY1 and BY2, because when we combine this, we will get B1. BY1 plus BY2 is actually equivalent to B1. CY1 and CY2, because CY belong to one is BC, another one is CD, so we should put different label because the total C1Y plus CY2 is equivalent to CY. Okay? Do you have any question? If you have a question, you can ask in the chat box. Okay? So beside element, we also have join. So we have BY and CY. This is CY. Okay, this is CY. And always remember that join moment is opposite with member and moment. Join moment is always opposite with member and moment. So if at B for member AB, okay, it is always opposite. It is always opposite. So it will be like this. Okay. No. It will be like this. Opposite. Clockwise, counterclockwise. Opposite. Okay. Join moment. This is for join. This is for join. This is for join. Okay. And all this is for element. All this is for element. So this will be, okay, this will be BY. This will be CY. So this BY is actually BY1 plus BY2. And this CY is actually equal to CY1 plus CY2. Okay, and the moment is always opposite. The moment is always opposite. Remember the concept. The joint moment is opposite with member and moment. The joint moment is opposite with member and moment. Joint moment is opposite with member and moment. Okay. So you need to remember the concept. Okay, member and moment. Okay, the sign convention that we assume for moment distribution method is clockwise, representing n moment, which is actually the moment towards element. Moment towards elements. Okay, okay, the green, the green. Okay, the first assumption that we made, okay, is member and moment towards. That is why we call as member and moment. It is towards member. Towards member. The moment is assumed as positive. Okay, positive towards member. Okay, this is the first assumption. Anyway, this member and moment will be depend on the fixed end moment that we get from the loading, okay, the external loading and the support settlement. And the support settlement. So this is actually the idea, okay, about the member and moment, okay, member and moment, okay, for moment distribution method. Okay, always remember that for I put here the join, okay, join B and join C in order to show to everyone that the moment that we distribute in the table is a join moment, where the join moment is actually opposite with member and moment. And if we have to draw the free body diagram for each element, it is like this. So in each element, there are vertical forces at A and B. Okay, vertical forces at A and B, for example, and it has also moment at A and B. So when we want to analyze the shear value after we have get AB and BA and AB and MBA from the table, so we have to apply this diagram. And to analyze this diagram, it is just like we analyze simply supported beam. Okay, this is the case where AB is okay referring to this question where there is no external loading on member AB. And on member BC, there is a point load which is located at the center. So I have put actually here 140. Okay, 140 that is subjected at the center. Uh, and uh, and we need to calculate FEM as the first member and moment. Okay, for member BC, and we need to put into the table. And then for member CD, it is subjected to 45 kilonewton per meter along member CD, and the first member and moment for member CD will be depending on the value, the FEM value. Okay, the FEM value. And don't forget to consider the support settlement for member which is located at position D. The support settlement located at position B means at support B, okay, that we need to consider as well. Okay, we need to consider as well. So this is actually the free body diagram. So let's look at the diagram for fixed end moment. So for fixed end moment due to loading. Okay, fixed end moment due to loading, we have fixed end moment for member BC and for member BC and for member CD. Okay, so the easiest way to do, I show to you now the easiest way to do. Okay, by assuming that both ends are fixed. Okay, even though at D it is pin support, doesn't matter, we can assume as fixed. Okay, at fixed, and later on we will find that the total moment in the table is equivalent to 0. Okay, this is assumption that we made when we apply fixed end moment. Okay, so this is point load 140, and that is UDL. Okay, this is member BC, and this is member CD. Okay, so this is 45. This is 5 meter. This is 2 meter and 2 meter. 140 kilonewton. So moment, fixed end moment is not sign convention, but it is behavior. Okay, it is behavior. So this is the behavior, the blue. Okay, the blue arrow. Okay, the blue arrow representing the fixed end moment for loading. And we need to understand also we have fixed end moment due to settlement. So we also have fixed end moment due to support settlement, which is due to delta. Due to delta, so in order to identify the behavior, identify the behavior, so we have to draw the beam and the settlement. The beam and the settlement. Okay, the beam and the settlement A, B, C, and D. When B is settled, it is settled like this. So we will have triangular. We will have triangular. Okay, we have triangular like this. Okay, delta always perpendicular with member. Delta always perpendicular with member. So what most important, we must understand that beam is a horizontal member. So the horizontal line is the reference line. And we need to measure the angle from original line. Okay, this is the angle. This is the angle. Okay, so the angle for, okay, AB, member AB rotates clockwise. AB rotate clockwise. AB rotate clockwise. And BC rotate counterclockwise. And by understanding the behavior, from this we know that we should get FEM, okay, FEM, which is uh, to counter back. Okay, so means that if angle is positive, FEM must be negative. Okay, so this one FEM will be positive because it must be counter clockwise. Okay. Okay, this is actually the things that everyone should understand about the fixed end moment, about the fixed end moment considering support settlement. So whenever we need to analyze beam with settlement, don't forget to include FEM due to loading as well. So what we need to do is we have to plus the FEM okay, length for CD is 5 meter. And there is P at the center, which value is 140. And there is W along member CD, and it is 45 kilonewton per meter. Okay, and there is a support settlement which is equal to 15 mm, and this is actually equal to 0.01 meter. Okay, in unit meter. Okay, so NE is given as 200 GPa and I is 50 exponent 6. Okay, 50 exponent 6. Exponent 6. So we need to have this whenever we have support settlement because settlement is given in unit meter. So we must have E and I in order to solve for the FEM due to settlement. Okay, so EI when we combine we get this. Okay, actually it is equal to, if we simplify we actually have this. Okay, it is 200 times 50. 200 times 50, it is 1230. 1230, 2 times 5 is 10. 2 times, so that is why we get 1 times 10 exponent 4. Okay, this is the same thing. Okay, so we have to create table, and in the table we should list all the members. Start from BA, AB and BA is the two N in member AB, and then member BC we have NBC, member C NCB, and we have member CD we have NCD and NDC. Okay, and I calculate the stiffness factor since EI is constant. Since EI is constant, so it is 4 divided by L. So length is 5. Okay, length is 5. So this is 4 divided by 5, equivalent to 0.8. And then for member BC, it is 4 divided by 4. It is 4 divided by 4. It is in terms of EI. Here I put EI. And then it is 3. It is 3. It is N pin. This is N pin. That is why I use 3 over 5. So we get 0.6. 0.6. Then I use this stiffness factor. Okay, 0.8, 1 and 0.6. Okay. Okay. 3 over 5, 0.6. So distribution factor for fixed. Distribution factor is 0 because this is fixed. This one is fixed. Okay, and distribution is equal, factor DF is equal to 1 because this is spin. Okay, spin. So the rest we have to calculate using formula. It is member stiffness divided by joint stiffness. Okay, it is 0.8. Okay, this is 0.8 divided by 1.8. 0.8 divided by 1.8. 0.8 from here and plus with 0.8 plus 1. Okay, so it is 0.8 divided by 1.8. We get 0.444. And the other one, it is 1 divided by 1.8. It is just like 1 minus 0.444. So we get this. Total this must equal to 1. Okay, so we use the same procedure to calculate the distribution factor for members CB. For CB it is 1 divided by total 1 plus 0.6. So we get 1 divided by 0.6. 1 divided by 1.6. 1 divided by 1.6. So we can also check here. It is 1. It is 1 divided by 1.6. 1.6. Okay, it is 0.625. And 1 minus 0.625, we get 0.375. Okay, same goes to the previous one. The previous one, it is 0.8. 0.8 divided by total 1.8. 1.8. So we get 0.444 minus 1. So we get 0.556. Okay. So this is the distribution factor. This is distribution factor. This is distribution factor. Okay, so for the fixed end moment, so there is no fixed end moment value for member AB because AB has no external loading on the member. Member BC, okay, member BC, so the formula is PL over 8. Okay, PL over 8. P is 140, L is 4 divided by 8. Divided by 8, so we get negative 70. Negative 70. So CB will be positive 70 because between BC and CB, due to external loading, we have opposite condition. We have opposite condition. Okay, and then we do the same for member CD. For member CD, we do the same. We calculate the fixed end moment, which is equal to WL squared over 12. W is 45 times L 5 square divided by 12. WL squared over 12, we get negative 93.75. So the other one must be positive. Okay, the other one must be positive. Okay, and then we move to FEM due to settlement. FEM due to settlement as okay, as I have shown here, the FEM must be both negative for FEM AB and both positive for FEM BC. Okay, for member BC. So that's why we can find that, okay, in FEM for AB, the formula is 6EI delta over L squared. Okay, 6EI delta over L squared, it is 6. 6E is 205, EII is 50, L is 0.015 divided by L squared. L squared is 25. Okay, 25. Okay, 25. So we get negative 36, negative 36. And then we have another one, 6EI over, this is should be 16. I just, okay, typo just previously. So now it is negative 36 here. This because when this 25, it represent to L squared. L, this is L squared. L squared. So we should get negative 36. And another one, L is 4. So L is 4. This is 4 times 4. Okay, 56. 56.25. 56.25, 56.25. Okay. So this is the FEM. This is FEM. L is 0.015 here. 0.015. Okay. This is 0.015. Okay, one negative, one positive. Negative and positive. So we get this. Okay. AB is negative for both. BC is positive for both. So it is 6E is 200 times 500 times 0.015 divided by L squared. Okay. So we must get the total. We must get total. It is, okay, negative 36 for AB, negative 36 also for BC, and then we get negative 13.75, negative 13.75 for BC. For CB we have 126.25, and for CD we have negative 33.75, and DC we have positive 93.75. Then only we can start, okay, start the first cycle in the table, which is this distribution, okay, which is distribution number 1. So for distribution number 1, remember to get the total moment. So I put, okay, the answer. Okay, the answer is 22.111. So let's check the answer together. Okay, it is, okay, the bold color, the bold one, negative 36 and 13.75. Okay, for joint B. Okay, this is total moment, joint moment. Opposite with this, we have 36 plus 13.75. Okay, the total is 49.75. Here is 49.75. We need to times with 0.444. And we get 22.1. 22.1. So of course we get the difference because this is using Excel, and of course Excel we consider all decimal places. Okay, when we have set to certain decimal places only, then we will find the difference. Doesn't matter. Okay, it is 22.1. Okay, so we check for the second value. We check for this 27. We check for the second value. So it is, okay, it is 36 positive because we want to have joint moment, which is opposite with member and moment. It is 36 plus 13.75. Okay, times with 0.556. It is 27.6. 27.6. Okay, 639, 625 doesn't matter. It is 27 point. Okay, 27 point. This is 36. 36. This is 639 doesn't matter. Okay, doesn't matter because just it is just because of decimal places that we take. Okay, so we check for joint C. For joint C, the previous is for, this is for joint B actually. This is for joint B. Now we want to do for joint C. Okay, for joint C. Okay, joint C. Okay, joint C, the joint moment opposite with this. Opposite with this. So we have here, opposite with this is negative. Negative 1, 2, 6.25 plus Because it is negative, we put positive. 93.75. Okay, 0.75 equal. Okay, equal negative 32.5. This is negative 32.5. We need to time with 0.625. 0.625. Okay, 0.625. Where is it? Okay, 0.625 times 0.625. We get negative 32.188. Okay, if we want to check whether the answer is right or wrong, okay, just do like this. Total. Okay, find the total. Total of this. Total of this. Okay, 1, 2. Okay, must equal to 0. If you want to check the answer, whether the answer that we calculate is right or wrong. It is 126.25 minus 93.75 minus 20.313 minus 12.188. Okay, it is 0.00 something equal to 0. Okay, it is just because of decimal places doesn't matter. Okay, so we okay, before that, okay, as after distribution, what we need to do, okay, for last value is 93.75. It is actually negative for the joint moment times with 1. So we get negative. Okay, so this value, okay, this value under distribution number 1, we have to carry over. We have to carry over. Carry over. Don't forget the factor. The factor is equal to 0.5 for all members except last one. Because the factor is equivalent to 0. Okay, the factor is equivalent to 0. So we have this and this and this, but this is equal to 0. The rest we have to divide by 2 or times with 0.5. So we get, okay, like what we have here. And then we have to repeat to the next cycle distribution number 2. Okay, so after that we have to repeat the process again and again until, so this I have actually did until distribution number 5, distribution number 6. So I get this. Okay, this is actually the value, the moment that we get from the distribution table, and I want to paste here. Okay, so this is the value, the moment, the member and moment. So this is the end moment for AB. This is for BA. This is for BC. This is for CB. This is for CD, and this is for DC. And this representing pin, where it is equal to 0. Okay. So from this we can actually deduct do some calculation by consider all the moment we can draw the shear force diagram and bending moment diagram. The shear force diagram and bending moment diagram. So let's do it one by one element. Since I have shown to you, okay, here, this is actually the free body diagram for, okay, free body diagram for member AB, free body diagram for member BC, free body diagram for member CD. So I want to analyze it one by one element. Okay, I want to analyze it one by one element by using this form, this value. Okay, by using this value. So for element number 1, okay, for element number 1, it is AB, and AB, it is actually, okay, we have here AY and BY1. This is 5 meter, and the moment is negative, negative. And the value is 24.986 and 13.939. So by using static equilibrium, just like we analyze the simply supported beam, we can take moment at one end and find the vertical reaction at another end. So let's say I want to choose, okay, moment at B, which is equivalent to 0. So what we get is negative 24.986, negative 24.986 minus 13.939 plus with 5 AY. Okay, this is equal to 0. So this is AY equal to 24.986 plus 13.939 divided by 5. So this we get 24 24.986 plus 13.936. Total we divide, it is 7.78 kilonewton. So what we get? What we get is actually, okay, the BY1. So by taking this, so we get BY1 is equal to negative 7.78 kilonewton. So for the shear force, so what we get is actually like this. Okay, we get like this. Okay, this is AB. Okay, this is actually 0 value, positive. Identify or draw the bending moment diagram. And the first bending moment value is this. This is the first bending moment value in the bending moment diagram for member AB. So for member AB, okay, this is member AB. It is negative value, negative 24. It is negative 24. Okay, somewhere here. Okay, so the value is 24, 24.986. We get from table. Okay, from table. Okay, so like this. Okay, and then we have to plus with the area because this is plus. Because this is plus, so we have to plus the area. So start with negative 24. Okay, start with negative 24.986. We have to plus with 7.78 times 5 because the length is 5 meters. Okay, so we have to plus the area. It is 8. We get what we get 13.914 here. Okay, we just need to join this. Thirteen point nine. Okay, 13.9. So this is positive. Okay, and this is BMD. BMD. So how we get that? So it is the first start with first moment. The first moment is negative 24.9 real. 5 times 7.78. So we get 30.9. And indicated at positive side. Okay, positive side. And it is positive side because, and it must be positive here, this must be positive because this is negative. Because the idea is for the diagram, whether it is shear force diagram or whether it is bending moment diagram, we draw the diagram start from 0, we end the diagram at 0. So where is the first point? This is the first point. Where is the last point? This is the last point. So we get 0 plus negative 24.98. So this is the second point. And then we get you get positive 13.9 This is after we minus by this. Okay, this positive 13.9, we minus by this, or we plus this, and this is negative. That's why it is minus. We get back to 0. So this is the right bending moment diagram for member AB. The right bending moment diagram for member AB. And basically, we can draw the BMD directly using the moment value that we get from table. Okay, just look at to the sign. Okay, just look at this to the sign. So like this. Okay, it is. Okay, this is the tips. This is the tip to draw the bending moment diagram directly without shear force diagram. Okay, the moment that we get from table. So this moment and this moment. Okay, look at the sign. Okay, it is negative, negative. So for AB, so for AB, it is negative and is negative and negative. Why negative, negative? Because from table it is negative, negative. So negative, negative means the first, the point of bending moment diagram is located here, here. And we just need to, sorry, this is a positive direction. Okay, it is negative, negative. Negative, negative means in this direction, negative, negative. Okay, it is negative, negative. So negative means point is located here and the point is located here. So we just need to join this. And the value directly we get from the table, it is 24.986 and 13.9. Okay, so it is negative and positive. Okay, so this one we draw directly from table. This one we draw directly from MDM table. Okay, so we get the same between this and this. Okay, we get the same BMD. So this is the shortcut where we can draw the BMD directly by using the sign that we get from the table. Okay, this is for AB. AB. So by looking at the MDM value, the end moment value for BC, member BC, we get positive and positive. Okay, we get positive and positive. So this positive and positive is actually the first point and the last point in the BMD, for member BC. It is positive and positive. So for member BC, okay, it is positive, positive. We know that from this we get the first point here, the last point here. But okay, since member BC has point load at the center, so we do not know whether the point load is located here or the point load is located here. Then this point must be determined using shear force diagram. Using shear force diagram. So using shear force diagram, what we need to do? We have to analyze first the BMD. Okay, analyze first the BMD. Okay, from here we get point load. This is 140. This is 2 meter, 2 meter. So this is member B and member C. So we have B, Y, 2, C, Y, 1. This is actually the label that we get from the first diagram. Okay, this BY2 and CY1. BY2 and CY1. And the moment, the internal moment. So the internal moment we get from this. Okay, it is positive, positive. What is the value we get from table? We get from table, it is 13939, 13939, 13939, and 140397. 140397. 140397. 140. Okay, so analyzing this, we will analyze this using static equilibrium. It is just like we analyze simply supported beam. By taking moment at C, we can get BY2. Okay, so it is taking moment at C. It is 130, 113. Is it 13? Yes, it's 13. It's 13,939 plus 140.397 minus 140 times 2 minus plus by2 times 4 equal to 0. Okay, from this we get by2 equal to what we get. Okay, it is 140 times 2. 140 times 2 or 280. Okay, minus 13.93, oh sorry, 939 minus 140.397. 397, okay, equal, we divide by 4. We divide by 4. Okay, this is 31. This is 31.416 kilonewton. So, of course, we will get CY1 equal to 140 minus 31. Okay, it is 140. So we get 108.5, 108,584. 108,584 kilonewton. Okay, so from this we get the shear force diagram for beam BC. Okay, start from 0. Okay, BY2 is positive 31. 0.416. Okay, go straight. Go until point load. And then minus, go down to the amount of 140. Okay. And then we get negative 108. We get negative 108. And then we plus back with CY1, which is equal to positive 90. Okay. This will be the last value. Okay. So this is positive. And it is negative. Okay, this is the shear force diagram for member B and C. Okay, this value is equal to 108.584, which is negative 108 plus, okay, plus back with this positive, so we get back to 0. Okay, having this, we will draw the bending moment diagram. Okay, bending moment diagram. Okay, the bending moment diagram. The first moment is 13.939. 13.939 is 13.939 plus with area. Okay, this is 2 meter. 2 meter. Okay, so to get the next point, okay, the next point at the center of member BC. So what we should do is we have to plus with the shear, the area of shear force diagram. It is 13. Okay, I need to close this first. This is 13.939. No. This is not the moment. The moment is 13.939. It is 13.939. We have to plus with area. It is 2 times 31.416. And this is equal to 13. It is 13.939 time plus with 2 times 31.416. It is 76.771. 76771. 76771. So this is the point. It is positive. So this is in kilonewton meter. This is 76771. Okay, and the next value means we have to minus this. Okay, minus this means that 76.771 we have to minus by 2 times 1 o this here 108.584. We get 140 somewhere here. It is 140.397, 114.4. 114.4. So this is the last point is 0. Okay. So this is the point. Okay. Okay. This is negative, and the moment is positive. This is the moment. Okay, the moment is positive. It is negative plus positive. So this is the last point. So the diagram is like this. Okay, we just need to join. Okay, join and join this. Okay, so just need to join this. So this will be the bending moment diagram. So this is positive and negative. Okay, so this is BMD for member BC. For member BC. Okay, for member BC. Okay, so okay, let's do the last. Let's analyze the last member. It is negative 140 and 0. Negative 140 and 0. So we know that the last point, the last moment will be 0 because of pin support. But moment at C is negative. So from that, so we want to analyze member CD. So we know that this will be negative. This will be negative. This will be negative and 0. Okay, it is negative 140.4 as well. 140.4 as well means that we know that the point must be here and the last point must be here. But we do not know whether, okay, whether the diagram, whether the beam, whether this beam has maximum moment or not. But we can do that. We can analyze that. We can identify that from the shear force diagram. This will be the last point at C and at D, and we may have the maximum moment which is located somewhere here or somewhere here. We do not know yet. Okay, maybe here or maybe here. So this will be determining from shear force diagram. From shear force diagram. So we analyze member CD. Okay, this is member CD. Okay. Of course, we have CY2 and DY and DY. So this is 5 meter. And moment we get negative. This is 140.4. Okay, or to be, okay, it is 140.4, 397. Okay. So from this we can determine actually the shear force diagram, but don't forget to put UDL. So for this UDL, it is 45 kilonewton per meter. Okay. So we have to identify the shear. Okay, we have to total moment at D is equal to 0. It is negative 140.4 minus 45 minus 5 minus 2 times 2.5. Like this, times 5 times 2.5 plus with 5 CY2 is equal to 0. So we get CY2 which is equal to, is negative negative. So we total all together divide by 5. It is 140.4 plus with 45 times 5 times 2.5. Okay, divide by 5. Divide by 5. So we get 140. It is 140.58 kilonewton. And we can get dy, which is equal to 45 times 5 minus 140. Apa ni? Ni? Tolong saya buat yang ni kat adik. Okay, so this is 45 times 5 minus 140 for 5 times 5. Okay, it is 225 minus by 140. It is 140.58. So we get 84.42. 84.42. Okay, so from this we can draw the shear force diagram, and from this we know that there is an intersection, means that there is maximum moment in the bending moment diagram. So from this we draw the shear force diagram. Okay, and it is 140. It is 140. 0 plus 140, so it is somewhere here. And then get this. So we just need to join this. Okay. Remember that the first point must be 0. It is 0 plus 140. It is 0 plus 140. We must minus by 225. That's why we get the 84 value, the negative 84, and then we plus back with 84. Okay, this is 84.42. This is 140.58. So this is positive. This is negative. Okay, and this is shear force diagram. This is shear force diagram. Okay, and using this, okay, we have to identify, of course, this distance and this distance. Okay, and this distance is equal to kilonewton per meter, means that it is kilonewton 140.58 divided by 45. Okay, the distance, the first distance is equal to, it is 140, it is 140.58 divided by 45. So we get 3.124. 3.124, and the second distance is equal to 84.42 divided by 44. And the total distance must be 1876. This is 1876. This is in meter. But we get from kilonewton per meter. So we get in meter. Okay? Okay. So now we want to draw the last diagram, which is bending moment diagram. For the bending moment diagram, there is a maximum moment. The first moment, okay, we will base on the value, the moment value at CD, which is negative 140. Okay, it starts with 0 plus with negative 140, so we get negative. We get the first value is 0 plus with this, plus with negative, this is negative. Okay, this is negative. We get the second value. Okay, to get the value which is okay located at the intersection. At the intersection. Okay, at the intersection. So we have to plus with the triangular. Okay, it is 140 point, it is 140.4. It is 140.4. And it is negative. We have to plus with this. Plus 140.4. It is negative. We have to plus with area 0.5. 140.58 and 3.124. And the answer is equal to is negative 140.4. We must plus with 0.5 times 140.58 plus times is 3.124. So this will be the value. 79.186. 79.2, it is 79.2 and it is positive. 79.2, 79.2 and it is positive. Okay, so this 79.2, 79.2 kilonewton meter. Okay, this 79.2, okay, we have to minus with the last one, the last triangular. Okay, and it is labeled as positive, so we have to minus this triangular. So what we should do is 79, it is 79.2 minus 0.5 times 1.876 times 84.42. Okay, check the answer. It is 79.2, we minus by 0.5 times 1.876 times 84.4. Okay, so we get 0. We get 0. So last value is 0. Then this is correct. So then we just need to join this. Okay. So this is straight line. This is straight line. And then curve. So curve and curve. Okay. So this will be positive side. This will be negative. So this is the shear force diagram. And this is the detailed solution, how we actually analyze the bending moment diagram, the shear force diagram and bending moment diagram separately. Okay, separately for this question. Okay, actually for this question, and of course we can, and of course we can combine all the BMD in one diagram. Anyway, you can also leave as this element by element. Okay, so that's all for this video. So inshallah we will continue in the next video. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.